So this is the last presentation before lunch and the cake cutting and the auction, so bear with. Today I'm going to talk about the CoCo1 and 2 Dragon support in additional memory. As many people know, the CoCo1 and 2 had between 4 and 64K of RAM. The Dragon comes in two main flavors, a Dragon 32 and a Dragon 64. Obviously the Dragon architecture is very similar to the CoCo1 and 2. But Nitrous or OS9 is available for those platforms, but only what's called level 1, which is the non-memory mapped or additional memory capabilities for OS9. So the project I'm going to talk about today is an opportunity to add additional memory to the CoCo1, CoCo2, and the Dragon machines to support OS9 or Nitrous 9 level 2, which includes additional capabilities and memory functionality. So this just gives you some explanation for the capabilities from a memory standpoint for the CoCo platforms prior to the CoCo3. Like I said, 4 to 64K. Virtual memory equals physical memory, so 64K. If you access a particular location in memory from the CPU, that's exactly the memory location on the motherboard that's accessed. Segmentation, there is just a very small capability for segmentation or banking in the machines that have the 6883 SAM chip. There is a way of mapping the upper 32K of RAM into the lower address space so that you can access it if you want to access RAM under the I/O. I/O, in case you're not aware, sits up at the top of the memory map in the XX region of memory. So you can't access RAM underneath that normally, but you can use the SAM to move memory down. But that's primarily your only memory memory expansion or memory mapping capability. So back in the day, there were a number of expansion options available. One was called Thunder RAM. It was a 256K RAM expansion for the CoCo1 and 2. By the way, not very much information on that particular capability online. So if you happen to have any information or you happen to have one of them in an old unit, I would love to get more information on that. One that does have more information is the J&R Banker board. A 256K version of it was published, technical specifications and schematics in the, let's see, that'd be the September 1985 Hot Cocoa edition. And then there was also a 512K version of the expansion board as well. Contemporary options, essentially the first two are just replications or reproductions of the Banker board. The last one is a more recent capability called the SAM X4 and the SAM X8. Those particular, so for instance, the SAM X4 is a replacement for the SAM chip, uses a CPLD to replace and offer some slightly additional video capabilities. The X8 offers the ability to do 16K pages and 2 tasks. So it gets a little closer to some of the capabilities that are needed to run OS9 level 2. But as indicated in the slide here, 32K is a pretty significant chunk of memory to page in and out of a system. That's basically the half of the 6809 address space. So running multiple tasks and whatnot, it's very tricky to get everything in to 32K pages at a time and be able to support multitasking capabilities. So there's two options that I looked at for adding proper level 2 OS9 support to the CoCo1, 2, and Dragon. The first one is to try and modify the existing OS9, or in this case, Nitrous 9 source code in order to support that 32K mapping of RAM. The problem, like I mentioned, is the granularity is pretty coarse, so it makes it difficult. Task management, with the exception of the SAM-X8, which offers the ability to switch between two tasks via hardware, none of the banker board capabilities offer task switching options. So in that case, if you want to do task switching, you wait for the interrupt, and then you'll have to basically remap everything yourself. There's no ability to swap easily between task or memory mapping tasks per task. The OS changes to support a memory size of 32K requires quite a bit of change to OS 9. It's not insurmountable. OS 9 was delivered for some platforms with a 4K page granularity, so 32K is not out of the realm of possibility, but it does require a significant update to the operating system to support that. There's also applications that expect, especially on 6809 or the CoCo3, for instance, they expect memory to be mapped in 8K chunks, and so those applications need to be modified in order to support mapping that is larger than 8K. There's also the tools or the capabilities that I mentioned on the last page really max out at 512K of RAM. So if you do want to support the full 2 meg that's supported in OS 9 or Nitrous 9 for the CoCo3, you need to make some more modifications to the hardware like the banker board or the SAM-X8 or whatever in order to support 2 meg of address space. So I chose the second option here, which is to modify the CoCo to support the existing capabilities for memory management that are in the CoCo3. 8K granularity is what's supported in the CoCo3. Nitrous 9 is already written for that, so that becomes our baseline. Task management, so currently in the Color Computer 3, there are 2 tasks supported. So basically a user level task and a system task, and the mappings for that are easily switched via what's called a task register. So you put in the value of the task you want to run, and then automatically all of the memory is mapped according to whatever task is running. As I mentioned, the CoCo3, although the GIME in the CoCo3 doesn't directly offer support for 2 meg, there is room in the registers that are used for memory mapping to support up to 2 meg of address space. And so systems like the Triad Plus and I forget Boys and Tech's product, but there's a couple 2 meg options that support that operation in the CoCo3. And so the idea is to continue that kind of support for the CoCo1 and 2. So again, just a refresh on CoCo3 memory specifications. 128K came standard out of the box. 512K was essentially a daughter card that you plugged into the computer. That's what it looks like over there on the right-hand side. There was a number of aftermarket options, but they all operated the same way. As I mentioned, 8K granularity for memory. And there was 8 of those, obviously, in a 64K address space across the 512K memory available in the system. And then the two sets of address mappings, hardware. The final piece is that there is a piece of shared memory that you can set up, a 256 bytes of what's called CRM, but essentially shared RAM that will appear in the same place in any memory mapping that's done in the CoCo3. So this becomes kind of our short list of capabilities that we need to replicate in the CoCo1 and 2. So just to give a little bit of example, I feel like for the color computer, the Radio Shack provided what I think is the most elegant and full-featured memory management unit in this era of computers. So some other ones had the ability to map ROM and RAM in specific locations into the address space of the CPU. But the Color Computer 3 offered this very flexible capability of being able to map any of the 512K address space in the standard CoCo3 into the 64K memory map of the CPU. And there were things that most folks don't normally think of being able to, or that you wouldn't normally use all the time, but there's still capabilities offered by the system. For one, pages can be mapped into both tasks. So if you need a piece of memory and you want to manage that it's shared between both tasks, that's possible. As well as another cool option that you might find valuable is to map a specific 8K chunk of RAM twice in memory. So let's say you want to do a copy from one place to another and offset by a certain number of bytes. You can actually map it twice into the 64K address space. Potentially limited utility, but still the flexibility is welcome, and so could be useful depending on what operating system. But as I mentioned in the bottom, 8K boundaries, that's your hard limit. Whoops. So I talked about the need to essentially replicate the CoCo3 memory management unit functionality into the CoCo1 and 2 and Dragon. This is a very important register. It's called init 0. It's at FF90 in the CoCo3, and there's 3 bits that are of interest to us. The first one is the bit 7, which is the CoCo bit. In the CoCo3, that particular bit is used to turn on or off certain video modes. So there's compatibility for the VGG that's more present when that particular bit is set to 1. When it's set to 0, there's some additional video capabilities that are available. Probably most important for the MMU is bit 6. So if you turn that to 1, the MMU is enabled. Most folks never see it any other way because the MMU is enabled essentially on boot in the CoCo3. And then, as I mentioned, this shared RAM capability, 256 bytes of RAM that's shared across both tasks, is enabled through bit 3, which is called MC3. That memory shows up at address FEXX, so FE00 to FEFF in both tasks' address space. The other register that's important is FF91, which is the init 1. The only bit that's important to us is bit 0, which is the task register. So 0 in that means task 0. 1 is task 1. And then as you can see down there, FFA0 to FFA7 are your MMU mapping registers for task 0, and FFA8 to FFAF are MMU registers for task 1. So that's how you set the various mappings in the system. So if we're going to replicate, this is what we need to do. We need to have over 64K of RAM available. We need to have those 2 registers, FF90 and FF91. We need the MMU memory mapping registers, which is, there's quite a few of them. That's 16 registers. And then there's some other things that we need that I didn't realize initially, but they're sort of necessary. They're kind of gotchas in the CoCo3 environment. Most folks don't know this, but CPU vectors on the CoCo1 and 2 point to locations in low memory on the CoCo1, 2, and Dragon. On the CoCo3, they actually point to that shared 256 byte area of RAM. So that's a different set of vectors. And then this shared space, we need to make sure that we support that shared space because OS9 makes use of that 206 bytes of RAM at FEXX. So I was talking last slide about the CPU vectors. So in the CoCo1 and 2, the CoCo1 and 2 and the Dragon use the SAM chip in order to do memory mapping. One of the things you may not be aware is that when the CPU fetches vectors from the top of memory, that's where it fetches its vectors like reset, software interrupt 1, IRQ, so forth. Those are accessed. The CPU is hard-coded to access those from should be FFF2, sorry, FFF2 to FFFF. So there's 14 bytes, 7 vectors. They're just 2-byte vectors. High byte, low byte is how they're stored. On the CoCo1 and 2, when the CPU goes to access those particular vectors, the SAM chip actually maps in the ROM, and the ROM that normally is mapped in is the lower ROM of so what you would think of as color basic ROM, or not the extended ROMs, but the basic default ROMs that come in. Those ROMs show up lower in the address space, but they are pushed up into the FFF region in order to read the vectors, right? And they are hard-coded in the CoCo1 and 2 and Dragon to point to memory locations in low memory. So like 0, 100, 0, 101 is where one of the vectors is pointed to. And on the CoCo3, those vectors actually point to FE, FEEE, and then some other values right up at the top of the FE range of memory. The idea, I think, for the CoCo3 is that the vectors would point to that memory, and then by sharing it or not sharing it, you could have vectors point to different locations depending on what task you were running. So OS9 depends on that functionality, and so we need to replicate that functionality. But number 2 is where we get into problem. On the CoCo1 and 2, unlike the CoCo3, there's no real good way to access the RAM under I/O. So when you get into the FF range of the CoCo1 and 2 memory map, you're accessing I/O registers or the CPU vectors at the top end of that particular space of memory. So getting the actual RAM that's underneath there requires using that SAM functionality that I described earlier, where you essentially, map the top 32K of memory down into the bottom 32K of memory, and then you can access the upper 256 bytes, let's say, of RAM in the memory map. But it's very cumbersome to use, and it's not very conducive to OS9. So we need to come up with another solution for that. And then, of course, as I mentioned, CoCo1 and 2 and Dragon, they did come in multiple memory configurations, but 64K was the limit. So here's the plan for what I planned, or what I was doing here. One is to replace DRAM with a, well, actually, there's a couple options here. One is you have a couple options to create the functionality that's needed to support the MMU capabilities in the CoCo1 and 2. The first one is to put your expansion in the DRAM sockets, right? So take the DRAM out, and you've seen that AJ has here out in the hallway. He's got some CoCo1s with the lids off, and you can see people have done some expansions on there where they've piggybacked DRAM chips on top, or replaced 4116s with 4164s or whatever. Huh? Oh, right, or the banker. All of those are done at the where the memory chips are, right? The problem with that, there's a couple problems. One is as Radio Shack modified the revisions of the motherboard, they changed the spacing of where the chips are, right? So on the CoCo1, they started out all across the bottom of the motherboard. And then later on with the F revision of the motherboard, they were squeezed into like the right-hand side of the front of the motherboard, so they're closer together. Then with the CoCo2, they moved to an optional 2-chip option, which was up towards or back towards the back of the board on the right-hand side. So you have a bunch of different options that you have to work with or work around if you want to do RAM expansions at the RAM socket functionality. And then, as I indicated earlier, if you have a need to access RAM underneath the I/O for any reason at all, you're very limited if you're in the RAM sockets as a function of doing your expansion, because you're limited to the capabilities that are supported by the SAM chip, and the SAM chip is what's going to limit you. So there's another option. You can add the MMU functionality to the SAM chip, which is what the SAM X8 and SAM X4 do. You can add the functionality there, but you still have to put some additional RAM at the RAM locations, so you have the concern around the motherboard layouts. And on the SAM chip, you don't have access to the data lines. You have access to address, but you don't have access to the data lines. So as far as handling registers and stuff like that, you're very limited. You either need to pull that data from somewhere else on the motherboard, or come up with a non-CoCo3 way of handling, like setting the task registers and setting the mappings and so forth. So it's kind of cumbersome. So the option that I chose is the third one, which is to put the additional capability at the CPU, right? The CPU gives you access to all 64K. You don't have to worry about limitations around the SAM chip. However, there is one drawback. The drawback is that the VDG, the video display generator, can only see memory that's on the motherboard. So if you have a 64K CoCo2, CoCo1 for instance, or Dragon, you have 64K of video memory available to you, but you do not have, unless you do some additional work, capabilities to move your video to anywhere within the 2 megabyte space. However, the video graphics video capabilities or need for RAM in the CoCo1 and 2 is much lower than it is for the CoCo3, right? You don't have a lot of the more complex, higher resolution with more color graphics modes that are available in the CoCo3. So as a result, I think the trade-off is worth it, and you can address this shortcoming, and I'll talk about that later. But for right now, the first iteration of the capability, I decided I was going to add the MMU at the CPU. It gives me most flexibility, and then we'll worry about VDG issues later on. So that on the right-hand side is a picture of the hardware. You can see for scale there is a 63 CO9E. So you do have just a couple chips added on. A lot of the functionality is using this what's called a CPLD, a complex programmable logic device. The RAM on the top is not actually, it is RAM, but it is what's called tag RAM, and I'll describe that in a little bit. The actual larger SRAM that supports all of the memory needed for the expansion is actually under the board. So this gives us the FF9X and FFAX register support, onboard SRAM, 55 nanoseconds, so that gives us ample speed. And then one thing we do need to do is, since we are on the CPU and we could potentially be accessing onboard memory, we need to make sure that we leave the motherboard in a sane state for any memory access that is not going to actually yield a read or a write to the motherboard, right? So if you're writing to a value and you decide you're going to write that value to internal or onboard memory, you need to make sure the motherboard doesn't see that as a write, or it'll corrupt the memory that's on the motherboard. Also on I/O, there are certain I/O registers that do things depending on whether you've read them, like status registers for the serial chips and whatnot. So you got to make sure that you don't actually accidentally read a value from somewhere in memory when that memory isn't actually going to be used, because that memory could be a status register, and then it might clear an IRQ or something like that. So the idea on here, and I'll describe in more detail, but the idea is to force the address bus to a certain state for any memory access that's going to be done on board. We'll implement those registers, bit 7, bit 6, and bit 3 of init 0. We'll implement the task register setting, bit 0 of FF91, and then we'll implement all 16 of those mapping registers at the FFAX address range. So in the picture right here, I talked about that chip up on the top. Actually, for CPLDs are great for doing logic, but they're not, so unlike FPGAs, they don't typically have RAM on board, right? So they just basically have flip-flops and combinatorial logic. So implementing memory within a CPLD is extremely expensive. So to that point, instead of implementing these 16 registers as functions on the CPLD, we actually create a second RAM chip, and we store those values in that second RAM chip, and that's the chip that's the IC that I showed on the last slide. So the key to offering VDG support is to create a hole in the address space. So the idea is that you have 2 megabytes or whatever of RAM on board this little daughter card that sits in the CPU socket, but for 64K of that space, you actually let the access go to the motherboard. That way you can access the RAM that's on the motherboard, then you can update things like graphics and whatnot. And also with updating that 64K, you also get access to the I/O, right? So if you didn't do that, then you could be running a program, but it couldn't access any of the I/O, and it couldn't and there would be no video updates or audio updates. So this created a little bit of a question in my mind as to where to put that 64K of where to stuff it in the larger address space. I chose the 3.8 to 3F. So for mapping reasons, if you have one of the task registers mapped to 3.8 in the register setting, that is the lowest 8K of RAM in the CoCo1 in this scenario. The reason I did that is because in the CoCo3, probably aren't aware of this, but the ROM, there's a 32K ROM on the CoCo3, and that 32K ROM, if you want to map it into, read it in using the MMU, you would map it in at it's 3C to 3F is how you map that ROM into the address space in the MMU, and so that led me to believe that I should treat the lowest, or I should treat the original 64K address space of the CoCo1 and 2 as belonging to pages 3.8 to 3F in the MMU. I mentioned this in the last slide, but the way we create sanity for the motherboard is for any access of memory that's going to be on board, we're going to force the address on the motherboard to FFFF. So it just looks like one of the null cycles that the CPU performs, because a CPU sometimes, if it's doing an internal operation, it will drive the address bus to FFFF. So we'll do the same thing here, and then anytime we're doing a write, we will convert that to a read on the motherboard. So for any memory access that's going to be done on this hardware device, the motherboard will see a read of memory location FFFF, which is normally the low byte of the reset vector for the CPU. So it's not going to impact any I/O. There's no write capability, so it's not going to change any data, and so the system will just basically ignore it. So there's two things that we found during initial testing. The one I mentioned is that the alternate vectors, so the vectors, the CPU vectors at the top of memory, I was thinking initially that we could just use the vectors that were defined in the ROM for the CoCo1 and 2 and Dragon. But hat tip to John Federico. He said, no, OS9 really wants to have like the software interrupt or whatnot that it uses. It really wants to have that vector point to the FE, FEEE, or FEF1, whatever the location is there. It really expects that. And we're trying to make as few changes to Nitrous 9 as possible to get this to work. So I replicated that capability. However, that's a problem, right? Because that is ROM in the CoCo1 and 2. And so what do you do there? Well, what I did in the hardware is I decided to take a small piece of the onboard memory and expose it at the vector locations, right? So when you turn on this alternate CPU vector functionality, the vectors that actually will show up when the CPU goes to fetch a vector is actually the onboard RAM, not the ROM that's pointed to by the SAM. The problem is that we need to be able to modify that memory, and we don't want to be able to do a write up at the top of the address space. So the way to get that to work is you turn on the MMU with the original vectors, you map that bank of memory somewhere else in the address space, update the upper 14 bytes to whatever vectors you want, then you remap it to the slot 7, which is the top of the 6809 address space, and then you clear bit 7, which originally I mentioned that bit was called the CoCo1 and 2 bit, the CoCo bit, and so normally it's set up to be 1, which means CoCo1 and 2 emulation or whatever in the CoCo3. So by setting it to 0, we're essentially saying, yeah, oh, by the way, we'd like to have some CoCo3 functionality, and the functionality we'd like is, in this case, alternate vectors. The other piece that we ran into an issue, so Tim Lindner, who works on MAME and whatnot, he was helping me with some memory testing, and we realized, and I think I mentioned this in a previous slide, we realized that as you were testing memory, when you were testing the onboard RAM, you would get a good test all the way up to FFF or FF00, and then all of a sudden the RAM test would start failing, right? Because the last 256 bytes of the address space in the CoCo1 and 2 is I/O. or CPU vectors, so it's not RAM. So what we did there is, or what I did there was I took another chunk of internal RAM that's not being used and mapped that in. So if you map the CPU, you map the F or E0 to FFFF region of memory, somewhere else into your mapping environment, and you go to access it, when it detects that an access on the motherboard would end up hitting I/O range, it actually shunts that request to onboard memory. So it's a little bit complicated, and I can describe it in more detail if you want. So those are the two kind of special things that we have to do for RAM in this particular unit. So here I just kind of give an example here. This is kind of an interesting one. So let's say that the CPU is requesting data from address 1000, and we're in task 0. The MMU reads the mapping at FFA0. That's the mapping for task 0 for 0, 0, 0, 0 to 1 FFF. That address range is represented by the mapping in MMU register FFA0. So we get 3F. Well, 3F is just a value in here. So what we do is we need to construct the actual memory address. One of the things I do in the system is I take the 3F, and remember 3.8 to 3F is supposedly that's where I mapped the original motherboard 64K. So to make it easier for the code to understand and myself to understand, we flip bits 3, 4, and 5 of 3F. So we flip them, whatever, if they're 1 in this case, because 3F would be 111, 111, right? We flip the upper 3 bits of that value to be 0, and that ends up becoming 07, which is the 7th 8K, or the 8th, 0 to 7, so it'd be the 8th 8K chunk in the motherboard, which is the top of the address space for the original CoCo1 and 2. So we try to access this. It would be the address, just like you do in the CoCo3. You take your value, you add it to the CPU request. You add those together, moving these 3 bits into the top 3 bits of your address. You get F000, and so that maps to F000 on the motherboard. So even though the CPU is asking for 1000, what the motherboard sees is a request to F000. And of course, that's just RAM or ROM, depending on how you have the system configured, the CoCo1 and 2 configured. And so whatever is at that particular memory location is returned. So to give another example that's a little bit more complicated, say that we wanted to access data from 1 FFF here. So we go through the whole thing, still get the mapping of 3F, we change it to 07, but then when we do the address, it's 071 FFF, which ends up being FFFF. So it is that last value in the address space of the CoCo1 and 2. Well, in that particular case, if we were to access that data, we either get the ROM vectors, right? Because if the alternate vector set is not on, then we get the ROM vectors. But if we have alternate vectors on, then we'll actually access onboard memory, not memory on the motherboard. So it gets a little complicated on how to access memory, but the big thing to remember is that there's a hole in the address space of this solution for memory that's located in the motherboard. So the good news is, if you want to play around with it, Karen Anscombe helped me put some code into the XROR emulator, which supports the CoCo1, 2, and Dragon. So you can try out this solution. Currently, the name of it is called CoCoMem Junior. Since it's going to potentially be used in the Dragon as well, I think I need to come up with a new name. But anyway, the code is available in the dev branch. So if you check out the dev branch of code and compile it, you can try out this particular capability. The Nitrous updates, I was hoping to demo actual Nitrous 9 level 2 running on the system, but we're still working through some items. I think there is the high resolution timers, or there's maybe a little bit of additional CoCo3 functionality that we need to add in order to get, or code around in order to get Nitrous 9 to run, level 2 to run on the CoCo1 and 2. So we're still working on that. Thanks to John Federico for the CoCo1 and 2 work. And then Pierre Serrat is working on Dragon updates. So the goal is to have Dragon and CoCo1 and 2 functionality. The project files are available at this location at GitHub. So if you're looking to see more about the hardware or the code that runs the actual CPLD, it's all at that location. And then there's another picture of the tool. So right now, the hardware functionality has been limited to that functionality supported by the CoCo3. However, the hardware itself supports additional functionality. So for one, in the CoCo3, the register, if I go back to that init1 register, if you look at that register, you'll see that the lower 5 bits of that 8-bit register, the only bit that's used in that is the lowest bit, bit 0. And so with that, you can set task to be 0 or 1. But they left space in the register to support up to 32 tasks. So nothing else uses those additional bits. There's so four additional bits that are there to support 32 tasks. And oh, by the way, OS9 has a maximum of 32 tasks. That's the capabilities that it supports. So this particular hardware adds that hardware capability for up to 32 tasks. And what that means is that you can do a mapping, and then you can just switch mappings just by changing the value in that register. So you can go, you have one mapping of 64K and then another mapping of 64K and whatever, and you can just quickly flip from one mapping to another without having to make any changes to the mapping set at all. Huh?
Big deal.
Yeah, that is. Now, obviously, OS9 doesn't support that right now. So for testing purposes, I've turned that off at the moment, but we can add it back in. The capability is there. The other thing that's there, which we could or could not enable, depending on whether there's value, is to create groupings of mappings. So let's say you want 32 mappings, and then you want another 32 that's slightly different or whatnot. We also have the capability of doing that. The final thing that this system is capable, so the actual board here has a maximum of 2 megabyte of SRAM on board. However, the register configuration offers the ability to extend to 16 bits in length. So that offers you the memory management capability to support up to 64 meg of memory. Now you do have to put actually 64 meg of memory on the board somewhere, and currently SRAM is kind of expensive, but the functionality is there. It's just disabled right now in the solution. Yeah.
So that brings up a question: do you expect to add this functionality over to the CoCo3 as well?
Well, I think the key would be, so I talked to the folks who are doing Nitrous 9 for the CoCo3. Currently, CoCo3 is really, or the Nitrous 9 is really kind of coded to support a maximum of 2 meg, right? So going beyond that, you can do like RAM disks and whatnot, because there were a couple, what I call back in the day, or classic expansion options. One was called CoCoZilla, which offered 8 meg of expansion for the CoCo3. And I think Ed Snyder offered a 8 meg memory expansion for the CoCo3 here, contemporary. However, OS9 doesn't support that, and they said that adding support for that requires a revamp of the task memory management functionality. So my thinking is that once this is working at 2 meg, then the next thing to do is to make sure that folks have 8 meg functionality on the CoCo3 so that they can revamp Nitrous 9 to support CoCo3 at 8 meg. And then the next thing would be to add the 8 meg capability, like have another version of this that supports 8 meg, which is easy. You can get 8 meg as just a single chip, so you can literally just solder a different chip to the bottom of this board. Going beyond 8 meg, well, that would be the next frontier. So I feel like it's kind of a leapfrog thing. So we'll do 2 meg on the CoCo3, which exists. Then we'll get 2 meg to work on the CoCo1 and 2 and Dragon. Then let's work on 8 meg for the CoCo3, and then once that's working, hopefully the changes will be minor, if none at all necessary. to add 8 meg to this functionality and then support CoCo or support 8 meg on the CoCo1 and 2, and then we'll switch back to the CoCo3 again and see if there's interest or value in moving beyond 8 meg on the CoCo3. Once it's supported on the CoCo3, it should be very, very easy to add that support to this solution. Okay, well, I kind of ran through that, and like I said, we're still working on it. You can check out, we've been commenting on Discord on the CoCoMIM, the CoCo Discord list. There's a CoCoMIM channel where kind of doing updates on where this is. And obviously, if you're interested, I can include you on emails and whatnot where we're going through functionality. The goal, obviously, is to get, as Mark Marlette at Cloud9 mentioned years ago when I was working on another memory expansion option, he said the true test of one of these is whether it'll run OS 9, right? So once, I mean, if it'll run OS 9, then you know you've got all the functionality in place. So that becomes the current goal, is to get OS 9 or Nitrous 9 to run on the CoCo1 and 2, the level 2 functionality to run on the CoCo1 and 2 and Dragon 64. So, questions? Yes?
I may have misunderstood here something, but if I understood right, there could be up to 64 megabytes, or 64 megabytes, up to 64K on the motherboard.
Correct.
And there's 2 meg on this new board.
Correct.
The lower 64K of the whole physical memory space is coming from the motherboard.
Correct.
Does that mean that the lower 64K on the 2 meg on this board is just not used?
Except for the upper 256 bytes of it? Correct.
Okay, so you're using that for additional things like that.
That's right.
I was just curious if there was any way to actually access that. Could you actually have 2.03 megabits?
You potentially could, yes. I mean, anything's possible, right?
Right.
I thought about that. The other thing that I thought about is, if you remember in the beginning of the presentation, I talked about the fact that the way that I decided to implement this meant that there's a limitation or a constraint that the VDG can only access memory on the motherboard. So if you go back here, I'll go back real quick and show.
What would be the feasibility of working it so the VDG could?
That's right. So if you see this picture right here, so just to understand how the banker board worked, I reproduced the functionality of the banker board. And so as part of that work, sort of the banker board is really a two-piece thing. It's got some stuff that sits at the SAM socket, and it's got replacement for the RAM, right? And so the SAM part, I moved to the CPU because it was easier for me. And then the RAM part, I didn't want to have to deal with DRAM and the way the banker board, they had like stacked DRAM with some wires and all that. That's for the birds. So I implemented this daughter board right here that converts the DRAM sockets to an SRAM pinout so that I could just put SRAM on here. And then you can see these address lines. These are the additional address lines for the banker board. So in one version of the CoCoMIM Junior functionality, I actually hooked these address lines up so that you could have 2 meg on board, and then you could have whatever you wanted on the actual VDG memory. So that was an easy way of saying, okay, you can't access all 2 meg that's on board necessarily, but we could put another 2 meg on the motherboard and access plenty of memory there, right? Because then the VDG would have access to that. The one thing I didn't mention that's, because it's a potential future option, but it's more work involved to figure out how to make it work. On this last slide here, so one of the additional hardware capabilities that I didn't put here because I'm still trying to figure out how to make it work is the CPU. Since we sit at the CPU socket, we could disconnect the CPU speed from the motherboard speed. So even though the CPU can only run, or even though the motherboard can only run at 1 megahertz on the CoCo1, 2, and Dragon, the CPU could potentially be running at 4 megahertz. Well, so can the RAM, right? Because I said I used fast SRAM on this. So it's indeed possible, assuming I can figure out how to make it work, to run the CPU at 4 megahertz and just slow it down when you do a do a memory access on the motherboard. So that means there's an advantage to have memory on here, because then you don't have to slow down to access it. But to your point, if you want to have more memory for the VDG, I think that daughter board functionality that I built for the banker board, we could use that. And then, I hate to be a heretic, but some of you may remember on the Commodore Amiga, there was what was called chip RAM or fast RAM and then slow RAM. So it was like two different kinds of RAM, whatnot, depending on whether the video system could use it or could see it or not. So you could end up with a situation like that where you have fast RAM and it's on board here, full speed, but you can't use it for video. Or you could do, slower RAM or video RAM, which is accessible by everything, but it only runs at 1 megahertz. Okay. Yeah. Sorry.
He had his.
Okay. Go ahead.
Okay. Does this block I/O for like microprocessors if you're going to do that?
So I guess I did forget to mention that. So I have reserved 3 bits at the top of every 16-bit task mapping. So the first 2 bits I've already defined. I mean, everything's up for discussion, but the idea is to create protected memory.
Yeah.
And so one of the things I also was thinking about is the ability to hide the I/O range from tasks. Like, you define what task is the system task, and then every task other than that wouldn't see any I/O in the FF00 to FFFF range. They just wouldn't see it at all.
Right.
If you went to access that memory, you'd only get RAM. That would be all you'd get. And then the only task that would be able to access actual I/O would be the task that you defined as the system task.
Right.
So that functionality is possible.
It seems to me like if you have, like you already have done that.
Yeah.
By not if you don't map block 3F.
Yep.
There's just no I/O in your address space.
Currently, the I/O is special cased so that it shows up everywhere at the top in memory. But you're right. I've got a note in the code. If you go look in the code, it says, "Hey, we could just map the I/O into one location, not every location, by making it 3F specific, right? So if you're 3F, then you get access to I/O, and if you map anything else but 3F, you don't get access to I/O at all."
So right now you're basically doing the CoCoFEST top 512K or top 512 bytes as constant?
Yes, as constant, right. That's actually the top 256 is constant, and then the next 256 is only constant if you set that bit to be like FF9 or FF90 bit 3.
Yeah.
If you set it to 1, then that's constant as well. Yes, so you could do that. But I could take the top 256 bytes and say, like I have some bit or something, and I could say, you know what, don't make that constant, right? But I was thinking about doing in conjunction with this idea of protecting it and saying, you're not able to just turn it off at will. If you defined a system task, then the system task would be the only one that could access it or enable it in that space. So, John?
Yeah, talking of the fast and slow RAM, an idea occurs to me, which may have occurred to you, okay, that if you had those 2 setups, that perhaps you'd want to be able to let the on motherboard be a shadow type deal. You actually write on the other a block of memory, you can do direct memory access to it. So we copy it back to the video.
Yeah, I thought about the bleed, the like shadow underneath or whatnot. My concern with that is, I mean, I could do that, but that doesn't work if I speed the CPU up, right? So so I'd have to make sure that you'd have to drop down slow to do both, right? I was talking earlier about maybe speeding the CPU up. The other one is, there's part of me that says the philosophy of the memory management unit was that if you wanted to do things like that, it might be better to have different pieces of RAM loaded in to the same address space in the memory, 64K memory, and then do like a quick, not necessarily a shadow, but do a store here and store there, and then increment store here and store there, or whatnot. It's possible to implement. I just am concerned about how I would enable that in such a way that people don't accidentally turn it on and then try to figure out why they were storing data here, and then all of a sudden their video gets corrupt or whatnot, and they don't understand, right?
Yeah, it was just a thought that I brought up. I figured you might have thought of it.
Mm-hmm.
Yeah, so if you did dual, then probably your task register would switch between the speed of the CPU. So if you had the motherboard mapped in, it automatically slow
Correct.
down.
Anytime, yes. Anytime you'd access motherboard for any reason, I/O or memory,
Yeah.
you'd have to stretch the CPU out so that you match a 1 megahertz cycle. Yep.
Yeah, I think you want, he wants to have rights to video memory only be on purpose.
Yeah. That's. Oh, what I found in doing this work right here is, first of all, it's already a little complex as to, okay, so you come in here, then you map to here, and then the motherboard wants it here, and so you're like, where it is, and it took us, like Tim and I, it took us days to figure out, like, why in the world are we not able to check RAM here, because we weren't anywhere near F0, we weren't anywhere near, well, but you were after you got through the memory management mapping system, right? And then the alternate vectors and some other things like that, so it was hard for me sometimes to figure out what actually was getting accessed, and I figured if it was hard enough for me, and I'm the one doing the hardware development, the software person is probably going to be like, I have no idea. So, so there is a trade-off there. But it is an option, definitely, to potentially pursue. Any other questions?
Not so much a question, but thank you. A lot of brain cells being burned.
Well, when I first was introduced to the CoCo, I got a CoCo3, and the first thing, memory and operating systems always been a big thing for me, and I just really thought that memory management unit was cool. And then somewhere I was at a CoCoFEST or whatever, and somebody's like, well, you have a CoCo3, you need a CoCo1. You got to have the whole family. And so I got the CoCo1, and then all of a sudden it's like, there's no memory management unit. I bet you I'm a hardware guy, I bet you I could add it there. But as you can see on I guess it's not really visible here, but I started the project in 2017, and I had this actual hardware is from 2018. So it's been incubating for a while. I gave it to a couple people to try and start working on OS9 support, but everybody's busy, and so those things didn't really get much traction. And OS9 is just not my core competency, so I really am dependent on somebody that's an OS9 hacker to get this to work. And then a lot of people that know OS9, level 2 anyway, they only know it in conjunction with the CoCo3. So I was very surprised, even Tim, which, kudos to Tim for helping me, but when he was writing MMU test code, which I need to put a link to his test code, it's like gimme MMU tester or something out there, it's a GitHub project. He would do stuff, and I would try to run it, and it would immediately fail on this code, and then I would go and do the whole logic analyzer, and the first one was, I was like, Tim, you have to actually set the MMU up, right? Because because you didn't think about it. Because in the CoCo3, by the time you get control of the system, the memory management unit's already enabled, and the mappings are already set up. They're already pre-configured for you. But on this, nothing's done. You got to do it all by hand. So there was just a lot of stuff like that where there was an implicit assumption that all of the capabilities of the CoCo3 had already done their work, and you were just coming on the tail end of it. Whereas here, if you want it done, you got to do it all by yourself. John Federico was working on the CoCo1 and 2 port. He had the same issue where, again, MMU mapping. I said, well, you got to enable the MMU, and he's like, okay. So he just flipped the bit, and immediately the whole thing just went away, right? And because he didn't have the mappings, because everybody knew when you boot a machine, they're already there, and he didn't have any of the mappings there. And so when OS9 was booting, it was expecting that the mappings were already there, a sane set of mappings, whereas he had to add the code to add them in during the boot process.
Because even you run into some of that if you do a game cartridge. You look at it, even if you start a game cartridge, some things are already set up for you.
Yeah, right.
And you're thinking about that metal, but you look at it, wait a minute, it's already set up.
Mm-hmm. Yep. Oh, I agree.
Hardware doesn't do that.
I was trying to think of the last thing. So anyway, so to finish the point, started it, it's been 8 years ago I started on this project. But John's super stoked. So if you have a chance and you know John, send him an email and say, John, keep going on it, because I'm sure he's got other competing priorities. I'm excited to have some Dragon support as well, so I'm hopeful that I'm trying to be honest, I'm trying to pit both of them against each other to see who can manage to get level 2 to come up first. I'm okay with either one, but it'd be cool to have. And Dragon's never had level 2 OS9, so this will be a first if we can get it going. So it'll be exciting, and then obviously once it's up and running, then it opens the door. Like, I don't want to make any changes to the hardware to go beyond what CoCo3 supports until we can get a baseline of functionality. But there's a whole bunch of cool features.
You don't want to make us jealous.
I think that's right. That's right. That is one of the things that came up, though, in some of the conversations, to your point, John, is once this is up and running, so if I can get it up and running and then I get the multiple tasks and maybe get the CPU to run faster than 1 megahertz, well, if I can run it more than 1 megahertz, I'll just immediately go to 4, because that's most 6309s can run at 4 megahertz. They're spec'd at 3, I think, the C grade, but you can usually run them at 4. So I'll go to 4. Well, CoCo2 or CoCo3 doesn't run at 4, so then you'd have, so technically then if I can get that going, then that would mean the CoCo1, 2, and Dragon would be the fastest CoCos, right? Except for CoCo3 FPGA or whatever. So yeah, you have to be careful about that. So I want all the CoCo3 people to be happy enough that they'll continue to help us add support for the extended address range. So I can't take anybody off. So we'll see. But I'm not going to pull an Apple and like 2GS and limit this, we can't go any faster than a CoCo3, because that'll take people off. We'll cross that bridge when we come to it. So,
Burn it.
Yeah.
well, thanks for coming. Lunch is now on your agenda.